Hi guys, it's Kirsten from WVIA here with a lesson on water. Today we're going to be learning about engineering water, what makes safe drinking water so that you can enjoy it at home, and what are some water sources that exist that engineers can tap into for this drinking water. We're also going to be looking outside at some of these examples of water, and then finally we're going to do an experiment using our own homemade filter to create as clean water as we can in a short amount of time. So we hope that you enjoy this lesson, and we're grateful that you are with us at Learn at Home on WVIA. So let's get started. We're going to start this lesson by talking about engineering water and what goes into the clean drinking water that we enjoy every day. This particular lesson is in conjunction with the show you're about to watch at 3 o'clock called Follow the Water by PBS. So let's get started with the engineering water, the slideshow portion of this lesson. So first, engineering and the water we drink. What's the connection? Well, first, we want to look at environmental engineers and what they're in charge of. One of the things environmental engineers are in charge of is finding good water sources. And another piece is that they treat the water to make it safe to drink. So they want to make sure that the water that they find is suitable for drinking as well. Now, civil engineers are in charge of getting the water to you. So there are two very different engineering jobs that are involved with water. Many types of water exist. So we want to talk about first surface water. So surface water is the water that moves above the ground. It's visible. So the first one we want to look at are streams, which is a body of water with a current moving. It's visibly moving. The water is visibly moving. And it's got defined banks where we see the stream ends on either side. So if you look at this picture, you'll notice that the stream has two sides. We see clearly where the water ends on either side. So it's contained in that narrow strip, and it's constantly moving. So we can see the flow of water movement there, especially with the white caps, as you can see. That's created because the water is hitting against those rocks as it moves past. Rivers are a natural waterway, and they're usually freshwater. There are some saltwater rivers as well. However, for today and for our purposes in this region, they're all freshwater. And they flow towards the ocean, a lake, a sea, or another river. We've briefly discussed the different types of water. We have streams, we have rivers, and we have lakes. What we're going to look at today is an example of, on a small scale, of what a lake would be. A lake is going to be a body of water that is not moving, so it doesn't have a current, and it's surrounded on all sides by land. So what we have here is certainly not a lake. It's much, much smaller, but it satisfies in terms of the definition of what a lake would be. And you can see that the water is not moving. It's stagnant. There is some flow of it, and it is constantly being fed by groundwater. So there are springs that keep this particular pond filled. But you'll notice that it's surrounded on all sides, and that will make it similar in many ways to a lake. Next, we have a stream, or sometimes called a creek, where I'm from, or a creek out here in Pennsylvania. This is a body of water, as we've said, that has the two edges visible, and water is constantly moving. So the source of this particular stream has just carried this water all the way down. You'll notice that it is nice and clear because DOM is not going to build up in a heavily moving, current-ridden body of water. So this is, I don't want to move too fast for you, but this is a stream. Here's an interesting example of dissolved organic matter. In this particular water, it's not really clear. It's not super murky, but it does have that characteristic brown tint, and you'll notice that there is a lot of organic matter in this water. So when we talk about DOM, or dissolved organic matter, you think about water that's not crystal clear. So there are things in the water that create that murky appearance. And this is just an example of that. And then I have another view of a stream. This is much smaller, but as you'll notice, there's a current, it's constantly moving, and the water is much clearer than what we've just seen. So there isn't as much dissolved organic matter in this water. I can see right down to the rocks. And that's a large part. The water is constantly moving, so there's no stagnation. There's no ability for the water to kind of grow that brownish color with the dissolved organic matter. It's all being flushed downstream, as you can see. The third surface water is what we call a lake. It's a large, relatively still body of water surrounded by land. Now, this is a good example of a lake. We also have lakes all over Pennsylvania. These are visible in terms of being surrounded by land, and the water doesn't move. It's relatively still. So we have the Great Lakes. In fact, you have Erie up in the northern part of Pennsylvania. That's one of the Great Lakes. It's surrounded on all sides by land, and it is relatively still. Now, groundwater is different than surface water. Groundwater is water flowing under the ground, underground, and it's stored in what's called aquifers. So those are, by definition, underground storage units for water, naturally occurring. The Ogallala Aquifer is located in the Midwest, and it is responsible for irrigating many, many crops. So if we look, the Ogallala Aquifer starts up in South Dakota, extends over as far west as Wyoming and New Mexico, into parts of Colorado, and then it comes all the way down south into Texas. Majority of it is in Nebraska, the Midwestern state, Nebraska. Portions are also in Kansas and Oklahoma. So that's a very large underground storage unit for water called an aquifer. And again, those aquifers are responsible for irrigating the crops that are so prevalent in the Midwest. Now, a term in engineering that's quite often used is DOM. It's dissolved organic matter. So water that is brown in color is likely filled with dissolved organic matter known as DOM, or it looks like to me DOM. DOM is composed of 50% carbon. Now, carbon is practically everywhere. In the pencils you write with, the human body is 18% carbon, and all of the trees and soil on this earth all contain carbon. So this is a very common element. DOM has both positive and negative effects on water. So that dissolved organic matter has both positive and negative effects on water. First, the positive effects of dissolved organic matter on water is that microorganisms thrive in dissolved organic matter, DOM. Tiny things. What's a microorganism? A tiny thing that can only be seen by microscope. They love dissolved organic matter. It's food for them. So when you have the darker the water, the more food is available for these microorganisms. Now, if you have dissolved organic matter, you will definitely find microorganisms. A negative effect of DOM or DOM on water is that it has the ability to transport certain metals. One of the most dangerous metals transported by dissolved organic matter is mercury. When mercury comes into contact with microorganisms and water, it can be transformed into a harmful toxin. So that's why we do not drink brown, stagnant water. Although there's many positive reasons for it, for the microorganisms, it's not good for human consumption. Obviously, it contains mercury, it contains bacteria, it contains lots of other things. So, environmental engineers must keep this information in mind when choosing safe drinking water sources. Now, we've seen an example of a stream and a pond, which is, I guess that would be relative to a lake on a much smaller scale. We've also seen some dissolved organic matter. But what we're going to do next is we're going to create a water filter, much like the environmental engineers do in terms of creating clear drinking water. So we're going to act like an environmental engineer who's responsible for delivering clean drinking water to a community. But first, we have to make dirty water and get some supplies ready. So let's get started. Okay, like I said, first we have to make dirty water. So you need a Ziploc bag and you need some dirt, just some good topsoil from outside. Don't use potting soil, just regular topsoil. And so now we have dirty water. Now that's some dirty water, right? Next, we're going to create a filter so we can clean the water that we just made, that dirty water. So first you need a glass, and we have that here, a coffee filter, and half of a 2-liter bottle. So we have that as well. Next, we're going to put the 2-liter bottle upside down into the glass jar. There we go. And we're going to insert the coffee filter as well, because what we want to do is filter the dirty water to make it clean, like we're environmental engineers. Perfect. Okay, next we're going to put a little bit of sand and gravel into the coffee filter to act as a filtration system. Okay, first we're going to put the gravel in, and we want to put enough gravel to weigh down the filter but not clog it. Great. And next we're going to put a little bit of sand. Sand is a good filtration for the dirty water. Okay, a little bit more. Great. Next, we're going to take the dirty water and we're going to pass it through the filter. We're just going to put a little bit in. It's not going to filter it perfectly the first try. In fact, we're going to have to do it a few times before we get some cleaner water. But at least we can start with this first attempt. So go ahead and pour some of the water into the filter. Now, as we can see, the water is filtering through our filtration system that consists of the coffee filter, the gravel, and the sand. If you look at the bag to the left, that's our dirty water. If you look at the water seeping through our filter, it's still dirty, but it's definitely not as dirty as it was when it was in the bag. The jar in the middle is the filtered water, one-time filtered. The bag on the right is our dirty water. And now what we're going to do is we're going to pass the filtered water through the filter one more time to see what happens in terms of filtration of that water. It's also very clear that our water in the center has dissolved organic matter. So it is that brown murky color as opposed to clean drinkable water. So we're just filtering the water again. Okay, so as it's filtering, notice that it's a little bit clearer again. And it's certainly not the brown, dirty water that we saw off to the side. We're actually going to film one more time using this filtration, and we'll see how clean we can get that water. We're going to filter a third time. So we're going to place the middle jar, which is filtered twice, through the filter, like I said, a third time. Let's see if we can get clearer water even this time. Now, it probably doesn't help that I have a bluestone countertop, so there's a color tinge to it, but I think it's clear that the water is clearer now that we've filtered it than originally. So if we can show the bag of dirty water very quickly, just stand it up, that is what we started with. And if we look at the jar on the left, we have some clearer water. Now, this is by no means clear enough to drink. There's still dissolved organic matter in the water, but it's definitely, if we were to continue to filter the water through this process, we'll see that it's much clearer. And maybe you can put this, my assistant is going to put this underneath so you can see the color of the water. So it's definitely clearer than it was when we started. Okay guys, was that fun? Did you enjoy the information, the nature walk, and the lesson, the experiment? We certainly hope you did. Next on PBS, you're going to be watching Follow the Water. So now you've had a nice little look at some of the intricacies of water in terms of engineering, and we hope you enjoyed that show. Follow us again tomorrow at Learn at Home when we have more teachers, more content for you, and more educational programming on WVIA TV. Don't forget to go over to our webpage for cultivated educational resources that go with each of the lessons, as well as the programming that we've shown. And at night, make sure you join us for Storytime on VIA at the WVIA Education Facebook page when we read to the little ones at night, every night at 7. So again, thank you for tuning in, and we look forward to seeing you again tomorrow. Enjoy Follow the Water.
I was working for a nonprofit organization known as the Pennsylvania Environmental Council, and they had a regional office here in Wilkes-Barre. We were able to pull together a regional conference on abandoned mine reclamation in the summer of 1996 that helped to sort of facilitate and charter the formation of the Eastern Coalition for Abandoned Mine Reclamation.
EPCAMR and the Western Pennsylvania organization WEPCAMR are vital resources for the groups who make up the environmental community. Assisted by community leaders, local conservation districts, and representatives from the coal and cogen industries, they supply critically needed information.
Give them what they need and to make it easier for them. And I think that's what EPCAMR's charge is, and that's what WIPCAMR's charge is, to get the work on the ground. This mine drainage is flowing from what we call locally the Honeypot Mine Shaft, or the Susquehanna No. 7 air shaft discharge. What's flowing is about a 2,000 gallon per minute discharge of mine drainage, 20 to 30 parts iron that's contaminated in this particular reach before it comes into confluence with the Newport Creek.
Discharges like this one stain the landscape throughout the Pennsylvania coal region. For every orange stream we can see, there are miles of abandoned mine shafts we cannot. Enumerating them may seem impossible, but tools for the job may already be at our fingertips.
Utilizing existing resources and tapping the institutional knowledge of former coal miners, and by looking at those maps from the coal companies, from the Second Geologic Survey maps, from the federal government's Office of Surface Mining folio maps, we can then determine what the level of the water is in the mines. We might be better able to treat the water by helping to utilize some of those resources.
These documents of Pennsylvania's coal mining history are a Rosetta Stone for deciphering our subterranean makeup, a way to use our heritage to shine a light on future environmental progress.
Not only does it give us the underground geology and the structural geology of the coal that's been mined out, it shows us the flow patterns of the water weaving its way underneath the ground to get to lower elevations and to these discharge points. What we've been able to do is transform a lot of the two-dimensional maps into a three-dimensional format.
EPCAMR utilizes computer software to map the hydrogeology of flooded underground mines, presenting a perspective never before possible, even when men viewed these mines with their own eyes.
So many people, and not only in the Wyoming Valley, but throughout our region, just don't realize that the water is flowing right beneath their feet. in some instances, and this could help us predictively determine if there is potential for subsidence. We did a conference one time, and the theme of the conference was, what color is your watershed? The majority of those streams that you're going to see are this particular color of yellow buoy, orange. We relate when we talk to kids, it's no different than if you left your bike out at night. We ask them what it's got on it, it's got rust. It's land availability that we need and settle in detention time to allow water like this to have this iron oxide not deposit in the channel, but put it into a system that would allow that iron to collect in a way that we can harvest it. One of the things that EPCAMR does on a very small scale is to process and dry this by the 5-gallon bucket loads so that we can sell it to other manufacturers that might want to use it for wood stains, for trail markers and kiosks. You can actually reuse this stuff right back in the community that it came from. We would love to see larger companies come in and create these type of jobs that are green, but they're really orange, and they could be harvesting a lot of this iron oxide for a productive value.
If we can change the way we see the environmental conditions around us, we may find that the legacy handed down to us by our industrial forebears is changeable as well.
I was born and raised here in the Wileman Valley, seen these streams since I was 3 or 4 years old. We found not only through working with our local elementary schools and our high schools, some of the myths that are out there and some of the just misconceptions that you can't take care of this type of problem. It's a mindset that we're trying to change. We have this place-based philosophy that teaches the kids about the history within their own school district. They don't have to go far. They can go 2 miles and be at this stream or incorporate some type of environmental skits into learning about what this is instead of just ignoring it. And they'll know by the time they're done with us what the name of this stream is, what the mine discharge is, what coal colliery operated here where their grandfather probably worked. Turn around that apathy that they may have had or that negative attitude towards the streams, see them for their future productive value. We can get those students and teachers to be part of the solution.